Hello. Hi, my name is Toby Hocking. We had a little bit of trouble backstage, so I'm just wondering if there's an audience now, and if you guys are all interested to hear about data table. I wonder if somebody could say hi, if you can hear this. I saw a thumbs up. That's that's good. Okay, so I guess I'll get started now. So the title of my talk is using and contributing to the data table package for efficient big data analysis. And I had originally planned for about 90 minutes, but it looks like we're only going to have about 75 minutes. That's fine. So I'll try to get through just the most important parts. And yeah, the idea of this tutorial, it's to try to teach you about the basics of data table and why it's a really great tool for data analysis in R, and state of the art with compared to other tools in any language. And so as I go through the tutorial, I just like everyone to know that it's totally okay to stop and ask questions. I would encourage you um, to just speak out if you have a question, because I don't really see any chat or anything like that. So I wouldn't be able to see the questions if you just pop them up and type them. So please just say any questions orally as you go along. So first of all, who am I? I have a bachelor's, master's, and PhD in stats and math with an emphasis in machine learning. So I'm a CS professor since 2018 at NAU in Arizona, and since earlier this year at Sherbrooke in Quebec. I've been using R since 2003, so over 20 years, and I'm author of over 10 R packages. And I've a data table user since 2015 and contributor since 2019. I'm a PI on the NSF Pathways to Enable Open Source Ecosystems POSE project about expanding the open source ecosystem around data tables. So that's why I'm here today presenting about it. So overview of my talk. First, we're going to talk about what is data table, why is it so popular and powerful, and that's because of its efficiency. After that, talk a little bit about how we can use it in some big data analysis, and then how to contribute to data table. And I'd like to make a plug for our NSF project, which is financing translation projects where the translators that try to translate the data table documentation from English to another language get $500 US. There's also travel awards where you can get up to $2,700 US to talk about data table at a relevant conference. Also, there's lots of opportunities to participate in the data table community on GitHub, so I'll tell you a little bit about that at the end. So first, what is data table? You've probably heard about data frames, and so this is a two-dimensional tabular data structure. You can see example with 6 rows and 2 columns. With data frames, usually in R and the square brackets operator, we can do subsets with using the first argument of the square brackets, or selecting columns using the second argument after the comma here on the inside of the square brackets. And the data frame has had a big impact in other programming languages with different implementations like in Julia, Python, Rust, etc. And so an efficient implementation of the data frames in R is called data table. So it's just like the data frames, but a more powerful R code syntax using these square brackets I, J, by notation we'll talk about later, and importantly, a C code implementation. It's a R package that's been on CRAN for 2006. CRAN is the central R package repository. So it's been up there for almost 20 years. Originally created by Matt Dowle, co-author Aaron Srinivasan since 2013, and 50 plus contributors. So it's a pretty substantial project, and there's actually over 1,500 other R packages that require data table. So it's in the most popular half of 0.1% of all CRAN packages. So that's rank 11 out of over 21,000 packages in terms of how many dependencies it has. how popular it is in terms of other packages depending on it. Data table, if you know about the tidyverse in R, it's basically equivalent of the readr, tidyr, and dplyr packages. And so it provides some of the same functionality, but with a shorter syntax. So for example, in tidyverse, you would do these pipe operations with like filter, group by, and summarize as 3 separate functions. In data table, you can do everything in the square brackets operator here. So that's here you would do a subset using the first argument, a computation in the second argument, and then specify the group by as this third group by argument. And so another difference with the tidyverse is that usually the tidyverse packages have many dependencies where data table has none. So it's very easy to install, and tidyverse has frequent breaking changes, whereas data table ensures backward compatibility. So it's easier for users to upgrade to new data table versions. And there's some comparisons here that I link with other packages like in Julia and Python. You know, there's these guides where if you're coming from different frameworks, you know, you can see how to do it, some similar operations in data table side by side. So that's kind of useful. Also, there's these benchmarks. I'll be talking a little bit about benchmarks later, where you know, data table is really extremely fast, even compared to more recent newcomers in this space like DuckDB, which is implemented in C++, and Polars, which is implemented in Rust. So that's data table. So that's the first package, first section of the talk. What is data table? So is there any questions about the first section? I wonder if I can go to the chat and see if there's anything in the chat now. I wonder if anybody could just say hi and say that they hear me. I don't hear anything. I don't see anything in the chat either. See chat. We can hear you. Okay, great. Well, yeah, like I said, please feel free to shout out any questions. So why is data table so popular and powerful? And that's because of efficiency. So let's talk about why is it efficient. Number one, there's 2 different kinds of data table efficiency. Number one is the efficient R code syntax, which saves programming time. And so what is that? That is this square bracket syntax where we have this I, J, by, where you can do mostly everything in data table with using just these square brackets, where the first argument here, I, is equivalent of the SQL where clause, where it's going to show you on which rows you're going to do the query. The J, the second argument here, is the select or update in SQL, so what to do on the columns. And the last the third one here is by, where you can do group by what. So you can do different computations for different groups in your data. So for an example, in a tutorial, I'll tell you about analysis of this airline flight data set. Every row is a flight, and so you can, for example, here do a subset on just one of the carriers or the company AA. The second argument here, J, you can do a computation of how many flights there were for that carrier and what was the mean arrival delay. And here at the by, you can specify that you want to do that computation for every unique combination of origin and destination. And for some more complicated examples, how do I use data table in my research? I do machine learning research, and so this simple syntax makes it possible to do computations and make relatively complex figures very easily. Like for example, here I have a figure where I have a p-value computed in red between a new algorithm and some previous baseline. So I wanted to compute that p-value for each one of those baselines. And to do that, we have this data table code where, well, first to compute the mean and the standard deviations here, we can use this dcast, a data table reshaping function that I'll explain later, where all you have to do is specify a list of functions that you want to do, like mean and SD. And after that, yeah, to do the p-value computation, I did that using this syntax like this, where here I used I, J, and by again, inside of this .st, which is a subset of data table for a combination of this outer by here, by, and data. So I say that for every combination here of these different panels and different data sets, we'll do this computation of, for every one of the losses, which is not this new proposed one, we're going to do the t-test to compute the p-value, and we're going to do that for by every one of these other losses. So another example is I was recently teaching about decision tree learning algorithms, and so I did a data visualization that shows how the decision tree learning works. And again, for example, if you want to compute some of these different elements in the figure, you can use this data table I, specify you only want to do the computation for the validation set and the pruning path, and you want to do the computation here SD min value equals value, which mean leaves. This means we're trying to select the minimum of the validation error and also the tree that has a minimum number of leaves, and do that for each one of these two variables, the loss and the percent error. So it helps us do a visualization using these data table operations. And so yeah, if you wanted to go see it, that's what you would do. Let me go back to the presentation. Excuse me. So the other kind of efficiency, which is really important, is the C code that gives us really efficient computation time. It saves a lot of time in memory. So larger data sets can be analyzing using smaller computational resources. So I'm going to explain a few benchmarks here. And what we see in this figure is we're plotting computation time on the y-axis here as a function of the number of columns and so data size on the x-axis. So what I did is a benchmark of these CSV reading functions in R. So data table fread is our CSV function in data CSV file reading function in data table. And so here we have relatively small data sets with a few number of columns, and here on the right we have relatively large data sets with a large number of columns. What we see is that data table fread here is the lowest curve. It's below all the other ones, so that means it's got the fastest computation time compared to here read R, read CSV, and even read CSV arrow, which is kind of a newcomer on the scene. And so same thing if you look at comparison with tools in other languages. Like here, there's some popular tools in Python like DuckDB, Pandas, and Polars. We see that all when we compare the read CSV functions in the different languages, that data table fread comes out on top here for reading data tables with a large number of columns. And so that's for CSV reading. So if we consider another operation like summarization, I do a lot of summarizations in the machine learning research. So here I compare how fast data table can compute the mean and the SD and the length a certain number of times over every time 10 numbers. And we see that here data table is actually 100 times faster for this computation than stats and dplyr packages in R. If you try to do the same computation using different Python functions like pandas, polars, or DuckDB, you also see that data table is a little bit faster here, 2 to 3 times faster than these competitors. So data table is really state of the art in terms of a lot of computations you can do for data science. Here's another comparison in terms of writing CSV files from R to disk. Again, you see that fwrite, this red curve is the lowest one. That means that data table is fastest. And the other competitors are not quite as fast. Sometimes, like for example, here is actually 100 times, oh no, about 10 times faster, excuse me. And same thing if you compare with Python functions, right? So here, if you have DuckDB, Pandas, and Polars, the CSV writing functions here, you can write much bigger CSV files in the same amount of time here. The time budget here, this horizontal line is 0.1 seconds. So in that time limit, we can actually write 14,000 rows of data table, whereas you only could do 6,000 or 2,000 with these other packages. So data table really is state of the art, and that's the reason why people like it and why people use it, because it lets them do their analysis very efficiently. So there's a lot of people who say, Data table is the most underrated R package. It has saved me days in waiting for analysis to complete. Alex Flyax says somebody should just write a version of rstats data table for Python. And the story, nothing as powerful exists at the moment. And that's still true. There are some efforts to port data table to Python, but it's not really complete like the R version. What is Joey Reed's 7 favorite packages? Data table, data table, data table, data table, ggplot2, rstan.r. So finally, Jim Savage says, with great sadness, I was forced to start using data table today. So yeah, all this to say is that a lot of people are using data table because they need to have efficient data analysis. So that concludes my second section about like why do we use data table. And so finally, going to get into the how to use data table in this third section. Are there any questions though before we go on? Let's talk about that. Let's see. Hello, hello. Any questions before we go on? It says there's a break, so feel free to use the full 90 minutes. Great. Anybody? No, I don't see anything in the chat. Q&A. I don't see anything there. Okay, well, I guess I'll keep going then. So in this part of the talk, I'm talking a little bit about how to use data table. And so first thing you want to do is install it. And so here we have a typical installation in our install.packages data table. It's useful to get the release version. If you want to try the development version, you can do install packages with remotes and then remotes install from GitHub, our data table. There's a couple of guides here that I link in my slides. Here we have a data table cheat sheet, which is useful. It's like a one-page front and back kind of helpful reference of the most common operations you would do in data table. Getting it started in our Tinyverse edition is also a nice source of documentation about how to do the basic data table operations. So to create a data table in R, we just use this kind of data table, and you provide column names on the left-hand side of the equals, and then the values you want in those columns on the right-hand side. So very similar to data frames. I think I'll probably skip a few slides because we don't have a ton of time. So I think probably I'll go to this. How does CSV reading works? So here it is an example of reading data from this flights 14 data set. And to do that, we use the fread function. You give it the name of the CSV file name of the CSV file that you want to read, and you get back this data table object in R called flights. And when you see the printout of the data table, it's you see the first 5 and the last 5 lines, and you see all of the columns. And so cool thing about fread is you can actually give it shell commands like here, egrep. You actually run that egrep command before you read the data into R. So that if you want to read a subset of data into R, that's pretty useful, especially if you have a really huge CSV file and you don't want to read it all in. You can also read directly from an URL using this kind of syntax, fread, and then you give the URL that you want to download the data file from. And so, I think the main part of this talk is going to be about this square bracket syntax. So the first part is about here, how do we use this first argument I? And that one, basically you can refer to any of the column names that just specify what kind of variables you want to subset on, like this, origin equals JFK, month equals 6. Those are called logical subsets. You can also do integer subsets. You just want the first couple of rows or anything except for the first couple of rows, you use a minus sign. To sort the rows, you use this order function inside of the first argument. So here, You sort by origin increasing and destination decreasing. And actually, this sort function is one of the key secrets to the efficiency of data tables. So it's so efficient that actually it was adopted and integrated in base R in 2016. And so yeah, it's super efficient sorting that lets you do these by group operations very fast in data table. So there are some exercises that I'm going to skip for the amount of time that we have today, but I invite you to do the exercises on your own. You can take a look at my slides online if you search for my data table tutorial. So let's talk about the second argument in the square brackets, the j. So here you can, just like base R, use to specify some column names here, like arrival delay, either in quotes or without quotes. If you use the quotes, you get data table back. If you use not quotes, you just get the vector back. So depending on how to use that, you get a different result, different data type. And you can also put data table inside of the square brackets here if you want to kind of select a couple of columns. Another way of doing that is using this traditional C concatenation operator in R with these character vector of column names. So here selecting two columns from that table. You can also, here on this slide, we show you how you can select columns with a variable. So here, if we have a variable, select calls equals x comma y, which is a character vector, and here we have a table which is got columns named x, y, and select calls. So what happens when you do this? Actually, you're not selecting columns x and y, you're selecting the column called select calls. So if you actually wanted to use that to select the columns that are named in that variable, you would do this dot syntax where that means to actually evaluate what's in that select calls variable, and then you get the columns x and y back. Or you could use this with equals false instead of the dot. Either way works. So to select all of the columns except for 2, for example, here we can do all the columns except for arrival day and departure delay. Or we can use either the exclamation mark or the minus sign. Both give us the same result. Same thing when you want to select a range of columns. Here we can use this syntax with the colon, where before the colon we get the first column name that we want to select, and then after the colon we have specify the last column name that we want to select. And so what it specifies is here, starting from year, ending at day. So we get year, month, and day as the result. If we want everything except for that, then we can also again include that exclamation point or minus sign. So to rename and compute columns, we typically use data table inside of the square brackets, the second argument here. And rename, you would specify the new name on the left-hand side of the equal sign, and then the old name on the right-hand side. So here we're renaming the desk column to destination, and here we're creating a new column, air hours, which is air time divided by 60. To do summarization over all the rows, we can use functions that return just 1 or 2 rows. So for example, here, if we use mean inside of this second argument, we get just 1 row back. And here we note that we're using a dot. The dot is kind of an abbreviation for creating the new data table. So here in the previous slide, we used data table, and here we're just using dot. So that's just a kind of abbreviation to save typing. And yeah, here we use the range function instead of the mean function, and so we get 2 rows back, 1 for the min and 1 for the max. And so after that, that's how to compute using the J argument. We also can create and delete columns using the J argument. So let's show how to do that. So in base R, to create new columns, typically use either the dollar or the double square brackets operator. So we call this version with a dollar like the literal name specification, because you actually have to type that name next to the dollar sign. Whereas here with the double square brackets in R, you actually can provide the new name as a variable here. It's a variable with a string value next. So the new column name will be called next. And so typically, you can actually use this syntax with data tables as well, but typically in data table, we prefer these versions because it's going to guarantee efficiency. So here, to create the new column literally, we can specify using this colon equals operator, a new column name on the left, and then the new value on the right. And same thing here, we can do here using the set function. Here we specify the data table. J is the column name that you want to create, and value is the new value you want to put in that column name. So these are kind of the data table equivalents that guarantee efficiency. So sometimes if you use the base R operations, you actually have to create a copy of the whole table. Whereas with data table operations, you're only going to be ever creating one new column, and all the rest of the data is going to be staying the same. So that can be quite a big efficiency gain sometimes. So to create a column, as an example, we do, so for example here, a new column called air hours, colon equals air time divided by 60. And so then we get a new column here, air hours. And we can also delete a column by using this colon equals null. So null on the right-hand side means that we want that column to disappear. And so here, after we do that, we see that the air hours column is still there, but then we deleted the air time column, right? See the air time column between month and distance anymore. So here is an example of how you set to create or delete a column. So same thing like we just saw with the colon equals operator. Here you can specify the column name as a variable, like here example new. And so here the value in the column is high. So here after we're doing that set, we get a new column with values high everywhere. After that, we can delete it if we specify value equals null. So next, we can use I and j together at the same time to compute on the subset. So I wonder if we should skip this and go ahead for. Yeah, I guess we can just keep going. We're going pretty fast, so I think we'd probably be able to get it through all the slides. So, so here we see, and we're using I and j at the same time. So the I specifies that we only want to look at origin equals JFK and month equals 6. And then the j that we specify here is length des. So this length of one of the columns specify. So to compute how many rows we get back. And abbreviated way of doing that is using this dot capital N, which is valid inside of the data table square brackets. And we can also use this dot parentheses syntax to select or to compute multiple columns. So here we just compute a single value. Here we compute a table with 2 columns. Here we can do an update on a subset of columns by using I and then that colon equals operator. We call it the walrus operator because when you look at it sideways, it kind of looks like 2 eyes and some tusks going down. But yeah, so using either the walrus or the set operator, and if we can specify I at the same time. So here, for example, if we wanted to set the air hours equals 0 for if the distance was less than 100, you can see that here we can just do that update just for a subset of the data. And so here we have some exercises. Again, I invite you to do them at home. And here we go on to see how can we use j and by at the same time. So here, going back to the syntax, we haven't talked about this by operator, but this is where data table starts to get really powerful. So we can specify in one square brackets how to compute something for any unique combination of some groups. So for example, here we do square brackets, and here we use a comma to indicate that there's no I or no subset to do first. So the second argument here is what we want to compute. NumFlights equals .n. By equals origin. That means so for every unique origin, we're going to get the number of flights. We can add some more things inside of this dot parentheses here, like for example, mean arrival delay, and then we get a new column which has the mean arrival delay for every unique value of origin. So we specified by equals origin. So here we have specifying several different variables, right? So here you do by equals dot parentheses origin comma dest, and that means that we're going to use each unique combination of origin and destination here, and for everyone we're going to compute the number of flights and the mean arrival delay. So we can also do ad hoc or creating new by grouping variables inside of the by here. So here we do dot parentheses origin equals to lower origin to kind of convert the origin to lowercase. And then we get a new origin column here in the output, which is just a lowercase version. And then we have destination equals dest, and here we just renamed that column inside of the by statement. And again, for every unique value of these two new variables, we're going to compute the number of flights and the mean arrival delay. We can also use all three at the same time. So I, j, and by. So I give a few examples of this at the beginning, and this is sometimes useful. And because we can specify them all at the same time inside of square brackets, it's efficient, perhaps more efficient than some other R packages like tidyverse that make you specify these things in a pipeline. So for example, here, if we wanted subset on carrier equals AA, then compute for every unique combination of origin and destination, the number of flights and the mean arrival delay. Here, this is the resulting table. We get 24 resulting rows. Note that's a subset of the version that we had before where we did that computation. We got 221 rows. So you can also use DTI inside of J with by, which is often very useful. For example, here for every group we are going to define that using unique values of origin and destination. We're going to select the first row and the airtime and distance columns. So here we specify for the flights data table, we get the square brackets, and here again we use the comma to say that we're not going to use anything in the I to subset. Second argument, data table, airtime, comma, distance, square bracket 1. So here we're selecting the first row that results from the subset here of the unique combination of origin and dest. So for every unique combination, we're going to select the first row in these two columns. And we can also sometimes use this .sd. .sd means a subset of data for a given group. So SD is a data table. We can do any operations we want on it, like here, the last slide, we created a data table with just the airtime and the distance columns, and then use the square bracket 1 to get that first row. Here we could just use .sd square bracket 1 if we want to get all of the columns instead of just 2. And so then we get the same number of rows, but we get more columns. So how can we write to and read from CSV in chunks? I think I'm going to skip this. You can come back and take a look if you want. I think it's more important to talk about joins. So in SQL, we have the concept of a join. And in data table, this is implemented by providing a data table as the I argument. So when we do that, we're going to have two data tables, the one that's outside on the left-hand side of the square brackets, and then the one that's inside on the right-hand side. So you can think of this as a right join. So you're doing DT right join I, which means that at least one row is returned for each row in I with matching data from dt. So let's give an example here. So when you want to, for example, going back to the flights data set, for example, let's define 3 days as a data table with month equals 3, day equals 17, event equals St. Patrick's Day. You also have another birthday and Christmas at different days. So here we have a data table of 3 rows. What if we wanted to join that to the flights data table to see what flights happened during those 3 days? Well, so here we would do flights, square brackets, 3 days, and then we can use this on argument to specify which columns we want to use for the join. So on equals C month comma day means that we're going to look at the month and day columns here in the data, and we're going to select the corresponding data from flights based on those columns. And so what we get back is we got back some data for March 17th, some data for September 26th, and finally we get some missing data down at the end for December 25th, indicating that there were no flights that happened in December 25th. So this is the idea of the right join. We're always going to get at least one row for anything that we specify inside of this I argument in square brackets. And when there's no corresponding data in flights, we're going to get one row with NA missing value. So by default, we're going to return all of the rows that match. And so if you want to just get the first or the last row, you can specify mult equals first or mult equals last. So here then you get 3 rows, one for each of the 3 days that we specified in I. We could also use no match equals 0L, which is meaning to return 0 rows if there is no match instead of 1 missing row. So here using that same example, we get some rows for March 17th and some for September 26th, but we don't get any missing row here for the December 25th. Sometimes that's useful. Then you get an inner join instead of a right join. So if you want to join 2 tables using set key, so this is kind of a guaranteed efficient join. So if you do set key on these 2 tables, specifying the same key for each table, month and day, then we can use this square brackets, flights, square brackets, 3 days, and we don't even have to specify the on, because by default the on takes the common key between the 2 tables involved in the join, and that will give you the same result, and it's guaranteed to be super efficient, because the set key, what it does is it sorts the data table, and because it's sorted, it's able to exploit the structure of the sort on the month and the day columns to get that join very efficiently. So you can also join the other way. So join the other way would be like here, 3 days, data table on the left side of the square brackets, flights on the right or the inside of the square brackets. And so in that case, what we would get is a row for every one of these flights. And we can see that if we order here, I did an order on is NA event so that we can see that there is some missing values at the end. And we can see that there are quite a lot of rows with missing values because there's only, again, this 2 rows in this 3 days data table that corresponds to either birthday or St. Patrick event, and all the rest of them don't have any corresponding data in 3 days, so they get an NA value for the event here. So let's keep going. So here we'll talk about rolling joins. So here we talked about joins where here we want to kind of join the data here based on equality, trying to look up what months and days are equal to, in the flights data that are equal to the data in the 3 days data set. Here we can also think about rolling joins, which are super useful for time series data, and we have an efficient implementation of that in data table. And to illustrate that, we have an example. Here I made a scatter plot of airtime and distance from the flights data. And I posed the question, how to compute the histogram of distances. So histogram, basically we're going to make some bins on the distance, and then for every one of the bins, we're going to compute the the counts or maybe the mean or something. The first thing that we'd have to do is define kind of a grid of bin that defines the bin. So here I define a grid of every 1,000 units of distance. Here you define a data table with grid point and distance columns. And that's what I'm showing in red here. And so if we want to join that with the original data table, well, what we're going to do is we're going to be basically saying, okay, let's join all of these data points to the next matching red kind of grid line. Here, join these ones to the next one or the previous one. So that's called a rolling join. And we have an efficient implementation here. I use set key to specify that we're going to use this distance variable for the rolling join. And here all we have to do then is specify roll equals inf, and what that means is here we're going to be joining all of the data in here to all of the next or the data points here on the flight data to all the previous one, etc. If you want to go the other way, so here we're going to go to roll equals minus inf, and then you have all the data points here matching the next grid point, all the data points here matching the next one, etc. And you can also try to get the closest one if you do roll equals nearest. So here, all these guys are going to go to this grid point, all of these guys are going to go to this grid point, etc. 4,000 here doesn't have any, which are the closest, so we don't have any data in the 4,000 grid point category. When you take a look at the result of that join, you get basically all the same data that you had in flights data plus this new grid point column, which corresponds to whichever grid point it was closest to. We can also do a summarize after the rolling join here to answer the question, how do we do that histogram or summary? Here we can do by equals grid point, and then do a dot n to define a new num flights column, and then mean airtime to find mean minutes column, and then we say for every one of these grid points, we can get some number, which I'm displaying as these red dots here, the mean. Another related concept to the rolling join is this non-equi join. So when you specify in a data table that you have dot parentheses dt call less than I call here, you can use inequalities here like this less than sign, and that will result in a join that that obeys these inequalities between the two columns here respectively in the DT data table outside the square brackets, and some column here in the data table that is inside the square brackets. And to visualize that here, I define some rectangles in gray, and what we want to do is say, let's compute all the data points here that fall inside of those rectangles. And so the data points that fall inside of some rectangle end up being colored here. The data points that are outside of the rectangles are colored black. And so what we see is that here when we do that non-equi join, here we do rect dt join flights on, and here we specify min dist less than distance, max dist greater than distance. So this min dist and max dist, these are the limits of these gray rectangles that we've defined here. And so what we can see is that we get some new data table where we have some NAs if there were these data points here in black that didn't match any of the rectangles that were given. And you get the corresponding grid point here. For example, this 1000, this is one of these orange points here that did fall inside of that rectangle. So this non-equi join is joining all rows which satisfy any given inequalities between the two tables. So that's sometimes useful. And so here, I'm going to skip this section with the by equals each I. You can take a look at that later, but this is kind of like an advanced join functionality. And yeah, I'm going to go straight to this data reshaping functionality, which is super useful in a lot of different applications. I wonder, yeah, so this is kind of like a good point to stop and ask for questions. I wonder if there are any questions now that we can take. I don't. I see something in the Q&A. It says, okay, I'm conducting research using panel data where data set consists of 660 observations. with 7 independent variables and 1 dependent variable. Given this structure, can this data set be considered big data? Furthermore, is it appropriate to apply big data techniques such as lasso and ridge regression to the data set, or are these methods more suitable for larger data sets with a higher number of observations and predictors? Well, this is kind of not really related to the subject of my talk about data table, but you know, I think I don't know if the lasso and ridge are appropriate for your data set. You'd have to compute the tester, or you use cross validation. So I don't know. We can talk offline later if you want to talk about that more, but maybe we can ask a question. Is it useful to use data table in the small data situation where you only have 660 observations? I would say yes, because you still have this efficiency of code syntax, even though maybe the efficient computation is not as important in small data. Can you share the slide deck with us? Yes. If you take a look at the beginning of the tutorial, there is a link. I'll put that in the chat. Here I have a link, open link. There is a GitHub tutorial, I'm sorry, GitHub that corresponds to the tutorial. Here, I'll put that in the chat here. And in the first part of the talk, you presented speed comparisons with other popular packages. Have these speed tests been independently validated? That's a great question. And yeah, I think, yeah, there have been other, for example, I have some grad students who have done the test on their own computers. I've done it on my own computers. But if you want to try to do it yourself to see if it's true on your computer, you just got to go to my blog. If you take a look here, like for example, this one, d time, a time figures, or here, pandas dt. Here, if we go to this blog, this is actually a R Markdown document. And so you can see like all the code that I ran to run the comparisons. You can try to run it yourself and see if you get the same figure. All the code for my blog is on GitHub too. So yeah, everything is open source here. So if you want to try to redo this timing, for example, here's this timing about writing CSV file, and we show that it's faster than Polars, DuckDB, and Pandas. You can go ahead and see if that's true on your computer too. Of course, you might get slight variations between computers, but I suspect that you probably see the same trends no matter what computer you run this on. All right, any other questions before we go on? Here, I'll put that link too, just in case. All right, let's keep going then. So going on, let's see. I was going to talk about the data reshaping. We got about a half hour, so I think that's pretty good. Let's do that. Yeah, here it is. So slideshow. Okay, cool. So data reshaping. This is this really super useful concept where sometimes you have data which is in this called like wide format or long format, and you want to kind of convert from one to the other. We call that data reshaping. In data table, there's a function called melt for doing that. In SQL, you have a function called unpivot for going from wide to long. And so we'll talk about that first. This is similar to reshape function in stats package or the pivot longer in the tidyr package. So the melt, I like to motivate this by doing this, how to make a plot like this of the iris data. Iris data is this famous data set where we have measurements in centimeters for different flowers. We have length and width of petal and sepal with different species, 3 different species. And so here I make a histogram, and kind of then, if we wanted to do that with the ggplot system, we have to do kind of convert the data from the traditional format where we have sepal length, length, petal width columns to a different data table where here we would have different columns part and dim. So we can use the specify dim as the panel variable here and part as the panel variable here. And so how could we do that? We can do a reshaping. And to do that in data table, we use this melt function, where you give data table as the first argument, and you can either specify ID variables. Here, the ID variables are the variables that you don't want to reshape, or you can specify measure variables, which are the variables which you do want to reshape. And so what you get in using either one of those kind of code versions, you kind of start out, if you start out with 2 rows here, you end up with 8 rows here, where here all of these numeric data in these 4 columns end up in this one value column here at the in the output. And you can also specify the variables that you want to measure using this pattern syntax here. You can give a regular expression. Here, dot star means any non-new line character 0 or more times, and then the square brackets dot means actually a literal dot, whereas the dot outside the square brackets means any non-new line character. And so that means here it's going to match any one of these variables here that has a dot in it, and that's going to do that same reshape operation a different way. And kind of like the more advanced or the more recent way of doing this is using the measure function. So here, inside of the measure vars argument, we can use this measure function where you can specify here part, comma, dim, comma, pattern. And here the pattern has some parentheses. Inside the parentheses is what is going to be the data that gets mapped to the corresponding element of this new column that's created based on these names here specified in the first part of the measure. So here, we're going to capture the first part, sepal or petal, into the part column. And the second part here is going to be captured into the dim column. So that's either width or length. So that's why we see in the output here, we have 2 columns, part and dim, that we get kind of right away when we use this measure syntax with the melt function. Another way to do that is with a separator. If you don't like to use regular expressions and you can and you have some separator, you can do that. You get the same result. And to summarize, this reshaping is really super useful because then you can kind of get different plots and different formats. It's really useful for data visualization, especially this reshaping. Another way of using this measure function is using this value name keyword. So here I say measure col1 value name. So col1 would be like a literal column name like part. And value name is this kind of sentinel keyword that means here we're going to create a new column for every unique value that ends up getting captured here. So here it's the second part after separating with a dot. So that means we're going to get a new column named either length or width. And so here we get a new column in the output, length or width. So I'm going a little bit fast here. But if you want to see more information about this, please take a look at my R journal paper from 2021. It's called Wide to Tall Data Reshaping Using Regular Expressions in an NC Package. And so, yeah, let's keep going and talk about at the end of this. So this is the summary of the reshaping long using the melt function, and here's just a summary again comparing with other packages, polars and DuckDB, which are the kind of like popular newcomers. And we see that actually data table is quite a bit faster if you kind of make this timing of how long it takes to do the reshape, including the time for copying to and from these other data structures that you need to use polars and DuckDB. In data table, you have some really efficient operations that you can use that don't require any copying at all. And it's got some more features. So if you want more information about that, see this new blog that I wrote on the reshaping operations on the Raft blog. This is a community blog for the data table users and developers. So let's talk about now the decast function, which is the opposite of the melt function. So it's going from the long data to the wide data. And that's the equivalent of the SQL pivot function or stats reshape direction wide and tidyr pivot wider in R. So this decast function is super useful. First of all, you can use it to recover the original iris data if you did the melt operation here. We're doing a melt. And so now we have all of the iris numeric data inside of this value column. Well, what if you wanted to get back the original petal length, sepal length, etc. columns? Well, you can use this decast function to do that. Here, you use a syntax where you specify a formula where on the left side of the formula, you put all the different variables that you want to use to define the different rows. Here I put flower, so we get a new row for every unique value of flower, which is the same as the row number and the initial data set. And then on the right-hand side of the tilde formula, we say part plus dim. So that means we're going to get a new column for every unique combination of part plus dim, just like in the original iris data where we have sep equals dot, petal dot length, petal dot width, etc. And so that's how you could use it for kind of regular reshaping. Usually, I use it for aggregation more often. So aggregation meaning kind of like the group by operations we were seeing using the square brackets, but sometimes it's more kind of it's more convenient to use the decast formalism to do the summarization or aggregation. For example, here I can specify species tilde dim fun aggregate equals mean. So that means we're going to get a new row for every value of species, a new column for every value of dim, length and width, and then we're going to calculate the mean for every unique combination of both. And kind of the useful part about that is that you can specify several aggregation functions at the same time. So that's a really convenient way of doing multiple different aggregations. So here, fun.aggregate equals list min, comma mean, comma max. We're going to get columns for the min, also columns for the mean, and also columns for the max, again, for every unique combination of species and dim. You can also specify kind of some other more complicated stuff, but we're kind of running out of time, so I'm going to just skip through the rest of this stuff and talk about the efficiency of decast. We also have in the same blog, we did a comparison of how efficient is it to use, the data table reshaping function compared to polars and DuckDB, which are these kind of more recent alternatives in memory databases. And we see that again, data table, if you take into account the time that it takes to copy to and from these different data structures, you need to use DuckDB and polars. Data table avoids the copying, and so it's actually quite a little bit faster, about 2x faster here in this case, 2 or 3x. So, and it's also got some features which are, for example, the multiple aggregation, which is not present in the in polars, for example. So all these benchmarks here are reproducible. If you take a look at the blog, you can just rerun the code and see if you get the same result on your own system. And so, yeah, last kind of thing about using data table I want to talk about is how do you use data table in your own R package. So data table is already imported by 1,500 plus other R packages on CRAN as of August 24. To do that, all you got to do is put imports data table in your description file and import from in your namespace where you specify whichever functions you want to import from data table. And here, there's a couple of tricks about avoiding notes from CRAN. One of the tricks is that you can use this setting variables equals null in the first line of your R functions to avoid CRAN notes about no visible functions and variables. Other thing you have to be aware of is we have set DT threads, which controls how many threads data table uses for multi-threaded computations. A lot of kind of basic operations are computed using multiple threads in data table, and so CRAN only allows 2 for its examples and tests. So if you get that note, if you're using data table, you should just put this set DT threads 2 to avoid that CRAN note in all your examples and tests. And I'm going to skip those details. And the last part of my talk is about contributing to data table. Your help could make a big impact. Before I go on to the last section, I wonder if there's any other questions people want to ask. Again, I encourage anybody to speak up. New questions are added. I don't see that. Okay, so I don't see anything in the chat. So feel free to just speak up and ask a question if you want to discuss. So yeah, data table is an open source project, and so its mascot is a sea lion which barks R R R, and we have a video of that here on this slide. R R R. You can see them. You can hear them saying R R R. That's why we call it. We adopted the mascot as a sea lion, and so we have a community blog called the Raft, where we adopted that name because the sea lions often float together on the ocean surface in groups called rafts. That's a quote from the Marine Mammal Center in California. And so, yeah, I'd highly encourage everybody, if you're interested in data table, to take a look at the raft. We have some new blogs about different performance comparisons and different introduction tutorials, and you're highly encouraged to contribute. If you're using data table and you have something interesting to write about, please send us a pull request on the blog. That would be a nice contribution to our community. And let's see. If you want to get involved in development, you should take a look at our GitHub repository. We have an active issue and pull request tracker. So that's at github.com/r-data.table. About 1,000 open issues and about 100 open pull requests. So it's pretty active. If you have any time and interest, we definitely could use your help. So an easy first contribution, even if you don't know anything about R programming or the C code, try reproducing an issue, download data table, see if you can comment about if that issue was reproducible, post the results you got on your own system. It's very helpful for us to know if you can confirm or deny that an issue is reproducible. And so we have a very inclusive community. After you submit your first pull request, you'll be invited to join the GitHub group as a member, which means you could create new branches for pull requests in main r-data repository instead of your fork. And so now is a very exciting time to get involved, as we recently created a formal written document describing the decentralized project and community governance. So for a long time, it was kind of one of these benevolent dictator for life projects. And then recently in the last year, we moved to a kind of community governance model. So it's really everyone's welcome to contribute, and we definitely could benefit no matter what your level of expertise. And so, yeah, in the context of this NSF project, we have awards for translation. So, for example, here, we already have translation projects for Portuguese, Spanish, Chinese, French, Russian, and Hindi. And so, yeah, we're looking for a call for projects about Arabic. If you know any R users or anybody who's just skilled at translating technical documentation from English to Arabic, please put them in touch with me. And if you participate in a translation project, you're eligible for a $500 award to make the documentation and messages more accessible. And also we're open to other languages too. So these are the priority languages that we established based on the number of people who are probably going to benefit from the translation. But if you have other ideas for other languages that might be useful, please propose them. There's a call for proposals on the Raft blog. There's also travel awards. So we have money to support people to travel to conferences and talk about data table. If you ever wanted to go to like the International Use R conference or any other related conference like that where you have some people that would be interested to hear about data table, please try to apply for one of these travel awards. And so the criteria is basically you should give a talk about data table at a conference with a relevant audience. And again, the call for proposals, we made it on this Raft blog, so please take a look, and you could get up to $2,700 to support your travel. So a couple of other new interesting things that we're doing in the context of this project for making the open source community kind of easier to contribute to is we're expanding the testing infrastructure. So we're doing performance testing on continuous integration. So the idea here is we want to build the developer confidence so we can check if new code contributions will cause increased time and memory usage. So what we're doing is that we're running this kind of performance test here for every one of the pull requests. And here's a plot of n equals data size in some particular computation and as a function of the time. We also look at memory, but here this is just a plot of the time. And here we have 5 different colored curves, which correspond to different versions of data table that we're using to do the computation. And so we can see that there's kind of like this CRAN version, which is the same as slow, which is kind of got increased computation time relative to these other 3 versions. One is fast, base equals master, and then head. And so what this means is that here we have like kind of like a slow version that we know is like some kind of historical version that was slow for a particular computation. We ran the CRAN version that's currently published, and we can see that it's the same. So if we publish the new version that's on master on GitHub, And we can see that it's the same. It's getting faster. So that we kind of run these kind of tests now for every pull request to make sure that we have guaranteed better performance and we're not backtracking. We're not slowing down or getting more memory usage. The other kind of interesting kind of testing that we're doing these days is nightly reverse dependency testing. So to make sure that data table is compatible with all of the packages that depend on it, what we do is we run reverse dependency checks every night on the compute cluster. So there's, like I said, there's about 1,500 other packages that depend on data table. We run all of their checks every night with our recent development version. And then we have this report that summarizes any regressions. So here it says that with these packages, every one of these lines here in this table represents one of the tests that it passes just fine with the currently published version on CRAN. It's okay, but using the development version of data table, it doesn't work. Here, the check that failed is a test, and we do get bisect so that developers can kind of figure out why this is happening and go fix it. Because the ideal is that we want to make sure that data table is always compatible and that we're not breaking anybody else's code every time we publish a new version. That's really important for the community, and so this tool lets us do that. Even though it's really kind of a difficult computation, it takes about 2 or 3 weeks of computation time to produce every one of these reports. But we run it in parallel on a computer cluster, so we get the result in about 9 or 10 hours every day. So to summarize about data table, we have a concise and consistent syntax. It's fast and memory efficient. There's no dependencies, so it's easy to install, and there's no breaking changes, so it's easy to upgrade. So there's an inclusive user and developer community with opportunities to contribute, including these translation awards of $500 and these travel awards of $2,700. So with that, I think I'll stop. We've got about 10 minutes for questions, so I can take any final questions if anybody wants to say hi. Hello. I don't see anything in the chat. Okay. Well, I think in that case, I think we could do all done. So thanks everybody for your participation and comments, and I hope that you are all interested in the data table, and please get in touch if you need any more information about that.
Thank you, Toby, for that brilliant presentation on data table, and apologies again for the delay at the beginning of that session. Next up, we have the keynote from 3 till 4, and after the keynote, the data science track is kicking off again with retooling for the data era with Wes McKinney. Thanks again to Toby.
Okay, bye.